Very well. So we have the second talk, and the speaker is Barbara, I suppose. And she will be talking about full non-equilibrium model for multi-component flows under the generic equation of state. She's from Politecnico di Milano, yes. And she's working with a group of Alberto Guardone, also with Rémi. Okay, the floor is yours. 15 minutes.
Thank you.
I give you a notice of tutti.
Okay, welcome. Good afternoon to everyone. And in my talk, I will speak about multi-component or multi-phase flow, and in particular compressible one. So we start describing what are these flow fluids, and they are defined as a flow with more than one component that coexist, but there is some separation at a scale above the molecular level. And the other assumption is that the flows or the component of the phases are immiscible. And we have, for instance, interface dominated or separated flows where they are clearly separated by the interfaces, or we have dispersive flows where we have, for instance, bubbles or droplets in otherwise continuous field. The presence of the multi-material interfaces are one of the most important challenges from a numerical point of view, because across this interface, the thermodynamical and thermophysical properties of the fluids change in a sharp way. And moreover, these interfaces deform as the time evolves, so they are not fixed in space. There exist two broad simulation strategies to deal with them. The first one is the explicit tracking of these interfaces, so the position and the movement are tracked in time, or otherwise we have interface capturing method, in which the position of the interfaces are reconstructed according to some integral indicator. This is the interface capturing strategy is the one that we present in this talk. In particular, I will speak about the diffuse interface method, in which the assumption is that in each computational cell there are always all fluids, at least in a very small amount. In this way, we are able to use the same numerical method in all cells, independently from the fact that the cell contains only one fluid, or it disperses the fluid flows, or it has a clearly interface in the cell. The cornerstone of this class of method is the Bayern-Monsanto model, from which a class of models that are usually called N-type models, or two pressures, two velocities model, have been proposed. These models are also called full non-equilibrium because each phase is described with its own pressure, temperature, and energy. And in this way, we can use a full thermodynamic model for each phase. So if we have two phases, we have two full thermodynamic model for it describing the single phase or the single component, and we don't need an equation of state for the mixture. In this type of method, the indicator for the interfaces is based on the volume fracture, which is defined as the volume occupied by, for instance, a droplet or a bubble of a certain fluid in a unit of volume. The sum of all the volume fractures should be equal to 1, because we are not considering that there is vacuum in our fluid. So all the volume is occupied by one or the other. So there are several, as I said before, there are several N-type models. The one we consider in this work is a pressure-based Bayern-Monsanto type model proposed by me and Abgrall recently. And this model is composed by, let's say, without going into detail, we have basically three equations. One is the balance for the mass density, one is the balance for the momentum, and then instead of the total energy, we have the equation for the pressure. In the green box, so in this part, we have something that is very similar to the Euler equation, but for the partial density, for the partial moment. This model is valid for any equation of state because we have described the thermodynamic derivative and the speed of sound in the generic way, and we have only in this part here this interface speed of sound, which does not have any thermodynamic meaning. Is just a way to write the same variables that we have in the thermodynamic speed of sound in this way, where we have the pressure of the interface, so P uppercase I instead of Pi. This Pi here and the UI here are two terms that are needed to close the model, and we need to make some modeling choice. In this work, since the terms in the red box are the part that models how the phase interact one with the other, and they are non-conservative because they contain the gradient of the volume fraction alpha. And to have the model symmetric with respect to the phase or the component, we use simply some averaging of the velocity and the end of the pressure. The other peculiarity of this model is the presence of this quantity MR, which is a reference Mach number. This model is dimensionless, and in particular, the first equation doesn't change their shapes between the dimensional and the dimensional version, while the last one changes. So this is a dimensional, and the fact is that we use instead of having a standard scaling in which a density and the reference velocities are sufficient to scale all the equation, we need also a reference pressure, because we use this reference pressure to actually define our non-dimensional pressure as a non-dimensional variation with respect to this reference pressure here. In this way, we have these terms in front of some of the terms of the equation, and this is particularly important when we are dealing with weakly compressible flow, which are something that occurs pretty often dealing with, for instance, if you work with liquid, because the speed of sound, the speed of the fluid is usually much smaller than the speed of sound of the liquid. And so if we take this equation in the limit at the reference Mach number going to 0, we have only that some terms survive. And if we also combine this term with the volume fraction equation, we have the multi-phase counterpart of the incompressibility constraint, which for a single phase flow is the divergence of the velocity equal to 0. In this case, we have this expression, but if you sum all these expressions for the phase, what you have is that the divergence of the mixture velocity is equal to 0. So just to summarize the model, we have that this model is able to recover the correct scaling of the pressure oscillation in the incompressible limit, and we can describe each phase which is on the thermodynamic model. Moreover, the model here can be equipped with some relaxation terms. So we can add here other source term that can be used to model mechanical relaxation, so pressure and velocity equilibrium of interfaces, but also mass transfer and other physical processes. Well, yes, the presence of the pressure equation make easier the fulfillment of the non-disturbance condition, as we've seen in the next slide. So now let's speak about the numerical implementation of this model. We are implementing it in the SU2 framework, so we are using a finite volume scheme on a dual grid edge-based unstructured mesh, which is transparent if the mesh is 2D or 3D. For the moment, we are only working on the 2D case, but the method is already ready to be extended to the 3D. The discretization, the numerical scheme, let's say, are pretty easy. So we use an implicit Euler for the time integration, and we use Ruzanov fluxes for the convective terms. For the non-conservative terms, so the one that involve the gradient of alpha and that were in the red box in the slide before, we need a special treatment because we cannot apply a standard upwind scheme to this non-conservative terms, otherwise we'll have some oscillation. So we have developed the robust discretization basing on the so-called non-disturbance condition, which states that if we have a two-phase flow uniform in pressure and velocity of at a certain time step, it should stay uniform in this flow variable also in the next time step. So how you can proceed? Let's say without going into much details, basically you describe your equation in time and the convective part, and then you impose, let's say by construction, the fulfillment of this condition. What results is something similar to this one. So if we start with the density equation, which is the one that doesn't contain any non-conservative term, we can have its discrete version. We assume a uniform condition, and in this case, what you have is a compatibility constraint that also your volume fraction equation should satisfy, because the alpha rho equation contains also alpha, and so if you have an equation with the densities uniform, you have an equation for alpha also. Comparing this with the volume fraction equation, we have a discretization for the non-conservative terms in the volume fraction equation, which clearly depend on the discretization of the convective flux that we have used in the density equation. So the main drawback of this, let's say, approach is that if we change the discretization of the convective term, we have to change also the discretization of the non-conservative term. But the main advantage is that this procedure is robust. For what happened in the momentum equation, it's easier because we simply have that this velocity and pressure are uniform. We have that the non-conservative term should balance the gradient term, the pressure gradient term. And so we have this simple discretization which resembles the Green-Gauss divergence approximation that we use for the pressure. And then for the pressure equation, we simply apply by analogy what we have discovered for the volume fraction equation, simply considering that now we have the difference in the velocity instead of the simple velocity. Okay, now let's see some preliminary results, which are mainly validation tests. The first one is the advection of a water bubble in a flux of A. And so what we want to check here is that we don't have any oscillation across the multi-material interface, and this is what happens because we don't have any oscillation in the velocity and in the pressure. And this is the, let's say, the agreement with the exact solution. We have some smearing of the solution because we are using a Grusonov flux, which is first order, and so it's very dissimilar. The second test is again a validation one, in which we have the interaction between a shock in air and a bubble of helium. So in this circle there is at the beginning helium, while here there is mainly air. And yes, in this case the Mach numbers are not so small, and so we want to check if the scheme is also able to work with compressible flows, even if we are not really at low Mach number. And moreover, we can compare the numerical results with some experimental data that are available in the literature. In particular, we compare the position of the bubble after some time, and we can see that the front is, we have a good agreement on the front position, while yes, the shape of the bubble is not perfectly recovered. We think that this is mainly due again to dissipation, because we are using only first order scheme. Okay, so let's go to the conclusion. What we have working on is the implementation in SU2 of a Guardone type model, which is a full non-equilibrium model, and we are working on a pressure-based formulation. The numerical method, the numerical discretization is uses pretty standard discretization scheme, so a backward order scheme for time, and there is no fluxes on the convective term, but it is robust because it enforces this non-disturbance condition by construction. And it is applied to structure. Future developments concern of course, implementation of higher order discretization, at least second order, but we are also thinking to go higher order. And in this presentation, all the results are obtained with the Stephen gas model, while we want to implement and test also different equation of state. And yes, the very next step is the inclusion of relaxation terms to model instantaneous and non-instantaneous mechanical equilibrium activities. If you're interested, there is one paper about the method, and one is in preparation about the implementation in SU2. Thank you for your attention.
Very good timing as well. Open for questions.
Hi, thank you so much. From the conservative to the non-conservative scale regulation. That's something that we measure also in addition to the more standard feature. Species and birds, and technically we managed to get it to work on so could you also manage to get
Okay, so the question is asking if the formulation that was presented, has shown any issues related to stability and convergence. Is this the right question? Summarizing a little bit the long talk. Okay, thank you.
No, we don't have stability or convergence issue. But of course, we are using a non-conservative formulation, and so we know that we are making some errors in the approximation of the velocity of the wave propagation. So we know that if the Mach is higher than what we have shown here, we have some delay in the propagation of, for instance, of the shock. But we didn't have any problem in the convergence. However, we are not considering turbulence. We are only issues. We don't have any business effect. And the other fact is that we know that when you work with this kind of equation, your expected order of convergence is much lower. So with the further the flux, you have 0.1/2 order of convergence. If you have a discontinuity in alpha, which you always have, because otherwise you don't have any space.
Yeah. And we actually expect to flux energy exactly how over is now stored the edges, then you can access that
Maybe you can have this conversation on the side or tonight at dinner if you don't have any other answer. Sorry for the joke. Okay, thank you. Any other questions?
I can this information to show some simplification for compressor regime. Are we tested and integrated?
So the question is looking at some validation aspect and their implementation. Am I right in saying this?
Like this?
Yeah,
Yes, but this is something that is can be controlled because this parameter is something that is user defined. So this reference Mach number should express the global level of compressibility of your flow field. And so if you set it correctly, automatically you have the correct scaling in the incompressibility if you are weakly compressible, or you don't have any effect if you are fully compressible. But again, if you are fully compressible, probably the pressure formulation introduces some other errors. One possibility that we are, let's say, Giuseppe, we work on it, is to combine a pressure and the total energy formulation and to find a proper way to switch between the conservative and non-conservative governing equations.
Thank you. Any other questions? Maybe last one?
Incredibly fire, maybe. And the result that you showed are for the basis of separate fluid. It makes sense to have separate fluid. What would be the difficulties of using a single fluid with phase change governed by one and the same pressure?
So the question was about the difficulty to model, let's say, a single fluid but two-phase flow with mass transfer. Yes, the first thing is that we need to add the mass transfer in this model that at the moment isn't. And this can be done with, let's say, a source term with the chemical potential and so on. So theoretically, it should work without any problem. At least in the literature, there are models similar to this that work. The main problem is that in that case, you have to deal with the vanishing phase, because when you have a complete transition, you have that some phase, at least in some cells, disappear, and it is because the volume fraction got very small, close to zero. And this is not so easy to manage from a numerical point of view, because you have maybe something that is volume fraction 10 to the minus 8, and this can introduce some robustness and stability problem. There are to add some other techniques to deal with this vanishing phase. I don't know if this is what
Thank you very much. So let's thank once more the speaker. Thank you.